Okay, yeah. All right, so thank you for inviting me to give a speech here. So I'd like to talk a bit on our work in trying to control electromagnetic field for energy application. As a brief background, the ability to control electromagnetic field, which is one of the fundamental aspects of nature, is certainly extremely important in general. And in the context of energy application is also very important. Our primary source of energy, of course, is the sun, and the amount of energy that comes to us actually comes through in terms of visible and infrared light at a very high frequency. For example, this is the frequency of a green light. At the other end of the frequency spectrum, we do our energy transfer these days also almost entirely through electromagnetic field. For example, our AC power supply runs at about 50 to 60 hertz. So the scale of frequency that you look at it very easily for 13 or 14 order of magnitude in terms of the frequency scale. On the other hand, in spite of their similar differences, the fundamental equation governing sunlight is not any different from the fundamental equation governing the electricity that goes around in your transmission line. And they are all Maxwell equations. So consequently, the ability to think about how you will control electromagnetic wave can have a broad range of applications, both from the source of the energy to the utilization of the energy. With that as a background, I think in this talk, I'm going to just touch upon a few things that we've been excited in the past few years. And we will talk about some work about radiative cooling. And one of the idea of also using that similar idea for cooling inside the room. Then, as was mentioned, I'm going to switch gear to talk about some of the work on robust wireless power transfer. So let me start with the first part on radiative cooling. The basic idea here is to try to exploit the universe itself as a heat sink. Now, the first two parts of my talk actually rely upon this idea that one can control what's called thermal radiation. So I would like to maybe give you a brief introduction of the idea of thermal radiation first. So in fact, every one of us emit electromagnetic wave in terms of thermal radiation. I've shown you one prominent example, which is the sunlight. And the other example that you probably would be familiar with is either a fire or a tungsten light bulb that's heat up to a temperature of maybe 3000 Kelvin, and that also emit visible light. So those are the examples that you probably would be more commonly associated with thermal radiation. On the other hand, in fact, every one of us who has a temperature of about 310 Kelvin emits thermal radiation. And lastly, we can also emit thermal radiation to the cold background of the universe. So these are all electromagnetic waves. So if you can control it, you will have ability to influence how you access and exploit these wide range of thermodynamic resources. And in particular, as I mentioned, one of the interesting points is the universe itself. The universe, of course, is extremely cold. The temperature is about 3 Kelvin or minus 270 degrees Celsius. And something that's cold from a thermodynamic point of view is extremely important. If you have studied thermodynamics, you will know that the efficiency, the Carnot efficiency conversion limit, scales as 1 minus TL over TH, where TL is the temperature of the heat sink, TH is the temperature of the heat source. To translate, to have high efficiency energy conversion, you would like to have a hot source. For example, the sun at 6000 Kelvin, of course, is a great one. But you will also like to have a heat sink. And now the vast majority of the energy conversion process that goes on Earth use the Earth itself as a heat sink at 300 Kelvin. On the other hand, it is certainly important if you can use the universe instead, which has a much lower temperature as heat sink. And so that's the premise of what we are trying to build up, is really to try to benefit from the existence of such a vast thermodynamic resource. And the important realization is that, in fact, we have radiative access to the outer space. If you look at the transmission spectrum of the atmosphere is actually fairly transparent in the wavelength range between 8 to 13 micron. And this wavelength range happened also to be the peak black body radiation spectrum at 300 Kelvin. So as a result, in fact, every one of us, when we go out and have sky access, we are actually radiating heat out into the universe. And that process is fundamentally a cooling process. So while it was commented that this looks like magic, is in fact something, you radiate heat out of the universe, is that in fact something that every one of us will be doing every day or every night. So it shouldn't come as a major surprise that you can do cooling this way. Now, and in fact, people have exploited this effect for centuries in a technology called nighttime radiative cooling. If you take a black object, put it on top of a roof, and allowing sky access, it can cool to a temperature that's about 10 to 15 degrees Celsius below ambient. This is a very simple experiment that every one of us can do. You just need any black things would do. Okay. Now, of course, if you actually would like to do cooling, you would like to do it maybe at a time of the day where things are actually hotter, and that's when the sunlight is shining on you. So in other words, it would be far more interesting if you can actually do the same effect of radiative cooling, a passive cooling during the daytime. During the daytime, of course, any black object that you have would not cool spontaneously because the sun is heating it up. So as a result, what we proposed a few years ago is to construct a photonic structure that reflects all the sunlight, but that nevertheless still radiate very efficiently in the 8 to 13 micron window. And what we show theoretically is that this kind of object can reach a temperature that's way below the freezing temperature, even under direct sunlight. And it will also have a cooling power density exceeding 100 watt per meter square. So building upon this theoretical calculation, we then did an experiment. So in this experiment, this is carried out led by Ashwath Raman, whose picture is here. We basically construct one of these structures. This structure is constructed on top of silicon substrate, so that's inert. And on top of it has a silver mirror. And on top of the silver mirror, there are 7 dielectric layers. And these dielectric are made of silica and hafnium oxide. The main active material here actually is silica, or it's common glass. Silica has a phonon-platon resonance. The silicon and oxygen atom basically oscillates at room temperature, and that emits thermal radiation. And as a result, this structure actually has a strong emissivity peak in the 8 to 13 micron window. On the other hand, due to the silver and also the presence of nanoscale thickness dielectric layers, the structure actually behaves as a very good mirror in the visible and near infrared part of the spectrum. So it reflects about 96% of the entire solar spectrum. And this is a picture of it. You can see at least the mirror part of the operation for this particular structure. And when we put it on the roof and we have it tilt so that it actually faces the sun, and so at peak, it will have 900 watt per meter square of sunlight directly impinging upon the structure. And nevertheless, the structure will still get a temperature that's about 5 degrees Celsius below the ambient air temperature. So this is, in fact, the first experimental demonstration of any object that you can put under the sun, and it will actually spontaneously lower its temperature below the ambient air temperature. This work, which was published in 2014, I think it took maybe a couple of years before people come to see that this kind of thing is actually not too hard to do. And so in the past, actually in this year, there have been a number of experimental results by other groups that finally coming out that extends to new material system. For example, this is a group from Caltech, and also trying to scale this up. And this is some of the results of making these into a thin film form by a group in Colorado. And the cutest one, at least in my opinion, on the other hand, is this particular experiment carried out by Nanfang Yu's group at Columbia. So what they did is they actually study a particular kind of ant, I think called silver ants. This is an ant that live in the desert. And what they showed experimentally is that the ant actually has very high solar reflectivity and also high thermal emissivity. So it's exactly, the body of the ant exactly satisfies the theoretical criterion that we set out for daytime radiative cooling. So they speculate, of course they can't ask the ant, but they speculate that's what the ant is trying to do. So I guess in terms of originality, it's hard to compete with ant. But one thing that's in our favor is that if you look at the spectrum of the ant's body, it actually could not get a sub-ambient temperature because its reflectivity is not high enough. So in other words, even though our ideas or our originality does not compare, our capability to engineer the spectrum still is better than ants. So it's something that's good about us. One important question after we have done these kind of demonstration is how do you scale this up, and more importantly, how do you actually apply it in actual practical situation? And most modern buildings like this one are very well insulated. So as a result, cooling on the roof or cooling the roof itself would do relatively little to influence the footprint, the thermal footprint of the building. What you would need is a capability to deliver the coldness actually inside the building. And now, therefore, it is actually important to try to couple these kind of radiative cooling system with a standard air conditioning system. And in recent work, we have taken a step towards doing that. We have built up some of these modules. Each of them has about 0.4 meters square of coolers. And then we have circulating water pipe underneath it so that it will cool the water below the ambient air temperature. And that water can then be fed into the condenser side of an air conditioning system. It turned out that a few degree drop in temperature for water inlet temperature already can improve the system efficiency of these air conditioning system by about 10 to 20%. So as a result, two of my postdocs, Eli Goldstein and Ashwas Raman, have started a company, SkyCool Systems, in trying to push this further, hopefully into a commercially available system. Now, on the fundamental side, we have demonstrated, and also in all the experiments that people have published, a temperature reduction of about 5 degrees Celsius, so it's a few degrees. Now, one of the basic questions that one would be interested in asking is, well, how cold can you get in these kind of radiator cooling system? From a fundamental point of view, we are here trying to establish a thermal equilibrium to the universe. And the universe is at a temperature of minus 270 degrees. So therefore, suppose you have a completely transparent atmosphere only at a narrow wavelength range, you only need that at a narrow wavelength range, then you can construct a structure with emissivity spectrum that fit right in that wavelength range. And as a result, you should be able to get the temperature of the universe, which is 3 Kelvin or minus 270 degrees. That might be a bit optimistic in where we live. So you can take a look at the spectrum of Stanford, California. And the blue curve here is the spectrum. The peak transmission here in a fairly dry day is about 90%. And using this, you can then redo your calculation on what the temperature you're going to get. And that temperature, and we predicted in our initial paper, is on the order of 40 to 60 degrees below the ambient air temperature. So in other words, you could actually have an object that under direct sunlight in a summer day, and nevertheless that can produce ice for you without any electricity. And so this is at least demonstrating the temperature reduction is what we've recently done. Actually, Dr. Zhen Chen, who is sitting back there, did this experiment where he basically built a vacuum chamber around our radiative cooler, and to use the vacuum chamber to cut down all the parasitic heat gain. And in doing so, he was able to demonstrate a 40 degrees Celsius on average temperature reduction from the ambient through both day and night. So this corresponds to a temperature, of course, that are far below the freezing point of water. And that point to maybe an interesting opportunity to use this kind of thing for storage, for example, of medicine or for vaccines in an off-grid situation. And that's something that we are actually quite interested in further pursuing. So I've talked about using the universe basically as a heat sink, somewhere where we dump the heat to. On the other hand, anytime that we have a heat temperature gradient, we have a heat flow, we should be able to extract power out of that heat flow. The prominent example, of course, is the solar cell that exploit the temperature gradient between the sun and Earth in order to extract electricity. On the other hand, you also have a temperature gradient between the Earth and the universe, and therefore you should be able to get work out of this temperature gradient as well. So given that we already have an object that has a temperature below the ambient air temperature, at least conceptually, one can run a thermal engine between the ambient and the radiator to extract power. So theoretically, you can run a Carnot engine in between, and you can compute how much power theoretically you can get out of it. You will get something on the order of 48 watt per meter square, which is, of course, not large compared with solar power, but it's not a negligible amount of power either, especially in the absence of solar power. So the ability to extract power out of outgoing heat flow, in fact, has very interesting optoelectronic physics associated with it. So one of the work that we show here is that now if you just, at least conceptually, take a solar cell. So a solar cell is a p-n junction diode. When facing an object that has a temperature higher than it, is going to generate electricity. Now, if you take the same object and you face a colder environment, for example, facing the outer space, in this case, you are going to have a net photon flux coming out of the solar cell. And what we show, nevertheless, is that in this case, you can also generate electricity. So in other words, an outgoing photon flux actually, or we call it negative illumination, because there's a negative inflow of photon, will also produce electricity on the diode. So the physics of it can be understood in the following sense. Now, if you have a p-n junction diode, you have the recombination current that balance the generation current that come out the heat source having photon impinge upon the structure. At the equilibrium situation, when the temperature of the solar cell and the surrounding medium is the same, these two terms balance each other, and as a result, you don't have any net electricity generation. In the typical photovoltaic situation, you will have a hot heat source, and therefore the generation current is going to dominate over the recombination current. And as a result, you are going to have a current that flows from N to P inside the junction, and that gives you power generation. But on the other hand, if you have a heat source that's actually colder than the solar cell, then the recombination current in this case is going to dominate over the generation current. So again, you are going to have a net current in here that can be used to drive the external circuit. So as a result, if you plot out the well-known IV curve of a photodiode, the black curve here is the typical IV curve at equilibrium. The red curve is the IV curve for a photovoltaic cell where the black curve basically shifts down, and then in this quadrant, you will have power generation. The blue curve here is the case where the diode is facing a colder ambient, in which case the curve will shift up, and again, you will get to a regime where you will be able to generate net power out of the system. So the key effect here is that in both the positive illumination case and the negative illumination case, they generate power, but the sign of the current actually flip as you go from one to the other. So this actually has never been explicitly demonstrated. So we, Parsi and Fan and a postdoc in my group, then did this experiment. So what we did is we take an optical diode, a mercury cadmium telluride is a long wavelength optical diode, and we have that face an emissive surface that we can control its temperature. And for data processing purposes, we put a chopper there, so it's just a rotating blade. And depending on whether the blade is blocking the optical path or not, you will have the diode periodically seize or not seize the emissive surface. So as a result, now when the chopper is rotating, you should see that the current on the diode fluctuates. And so here is the experimental result. When the blade is blocking the optical path, you have zero current. And when the blade is open, then you generate non-zero current, both in the hot emissive surface case, where the emissive surface has a temperature higher, and in the cold emissive surface case, where the temperature is lower. So in both cases, they indeed generate current, the diode generate current, but the sign indeed flips, just like what we have predicted theoretically. So in this case, you can ask, how much theoretically can you get actually out of this setup, at least again in the same ideal case where you imagine that you are trying to do this conversion between a 300 Kelvin ambient and the 3K universe, and when your engine is sitting on the hot side. The analysis actually for this, which is very similar to the Shockley quasar analysis, give you a power density of 54 watt per meter square, which is already higher than the use of Carnot engine. And so we refer to this as the Shockley quasar limit for harvesting outgoing thermal radiation. But as is in the solar cell, where one can beat Shockley quasar limit, it will be interesting to ask what is the ultimate theoretical limit that you can do in harvesting outgoing thermal radiation. It turned out that you can define an exergy of the outgoing radiation in terms of the entropy and the energy flow outward. Given that the outgoing thermal radiation, the main benefit is for removal of entropy, you would actually like the removal of the entropy to be as large as possible, and that's really what gives rise to the possibility for extracting power. And if you do this calculation, it turned out that the upper bound for this is 153 watt per meter square between 300 Kelvin ambient and the 3 Kelvin universe when the engine is sitting on the hot side. And moreover, this limit, which is similar to the Landsberg limit of solar energy conversion, can similarly be realized by concatenating a Carnot engine and as well as non-reciprocal elements. So I think this results, on one hand, point to actually the existence of a fairly large exergy that's existing in outgoing radiation. And the other hand, in fact, currently, the almost complete lack of actual technology to be able to do so. So I think it's actually a very interesting question for further research. So up to this point, I have focused on cooling, passive cooling. In this case, we need the universe itself as a heat sink. Therefore, you have to go outdoor to be able to do passive cooling. One of the questions is, well, can one use some of these concepts of radiative concept for indoor cooling? For any passive cooling technique, the second law will tell you that the only thing that you can do is to get heat to go from hot place to cold place. You can't do any other things. Now, in the case of indoor, in fact, like what we are right now, our human body is typically maintained at a temperature that's above the room temperature. And so the objective of air conditioning system ultimately then is to be able to facilitate the heat dissipation from the human body to the environment. Now, as it turned out, in a sitting environment, which is what we do right now, about 40 to 60% of the heat dissipation from the human body is through thermal radiation. So as a result, if one can control the thermal radiation, you can actually facilitate the dissipation of body heat into the ambient environment and therefore reduce the amount of air conditioning that you will actually need to do. So in this sense, therefore, you would like to control the radiation properties of the things that we wear, which is textile. Conventional textile that we wear, for example, a cotton shirt, will block out visible light, which is by design, but it will also actually absorb and therefore block out all the infrared radiation from the human body. So from a heat dissipation point of view, it is suboptimum. Now, for pure heat dissipation argument, if you want to get the heat to radiate out from your body in the most efficient way, of course, you most likely the optimal solution is not wear anything. Given that this is not exactly the kind of solution that I'm going to advocate, what you instead should like to do is to construct a cooling textile that allow the thermal radiation to come out while still strongly block the visible part of the spectrum. So this is a work in collaboration of Professor Yi Chui's group and led by Dr. Paul Chun Shu in Yi's group. So we've constructed one of these material called nanoporous polyethylene. So polyethylene by itself is a visibly transparent material that happens also to be infrared transparent as well. And by introducing nanopores inside polyethylene, the size of these pores is on the order of a couple hundred nanometers. One can very strongly scatter visible light, and as a result, the nanopolyethylene itself now actually with the same material actually look white. The light just cannot go through. Visible light cannot go through. On the other hand, the size of these pores are much smaller compared with the thermal wavelengths of about 10 micron or so. So in fact, in terms of the infrared transmission is not any different from the normal polyethylene. So this, therefore, the center region here, therefore, is a material that allows the light, the thermal radiation to come out very efficiently while blocking most of the visible light. And we have done a thermal experiment. In this case, we will basically have a heater, a heating element, and with a certain amount of power injected to it. Now, and therefore, it will reach a certain temperature without any cover, and we've chosen the amount of power that inject to it such that without any cover, it will reach a temperature that's comparable to a human body of 33.5 Celsius. Then, if you, of course, covered it with cotton, you are blocking part of the thermal radiation, and therefore its temperature goes up fairly drastically. On the other hand, if you cover with the nanopolyethylene, as I'm talking about here, the temperature compared with cotton is a lot lower. And that's an indication that for the constant heat load, one will have a much better way to dissipate heat through radiation. And in fact, you can see that it's a radiative effect by taking a look at the infrared image. So you can see that in the bare case, of course, in the infrared image, you can see what's underneath. And if you have a cotton, then you don't see anything underneath because that blocks the infrared radiation. But with nanoporous polyethylene, you can still also see the object coming out. So this is an indication that there exist textile materials through which one can control thermal radiation for cooling purposes. And we have actually quite a bit ongoing work in really making this into a woven structure and also for generating actually cloths and also to make sure that one can maintain other important characteristics of textile. For example, breathability, weakening capabilities, and so on for these kind of structures. So we actually have quite a bit of ongoing work along those directions. So this concludes, I guess, the first two parts of my talk where the emphasis is on thermal radiation. In the very last part of my talk, I like to switch gear a little bit and talk about really going into very low frequencies. These are frequencies maybe megahertz or even lower, where we're trying to do here is a technique that we call robust wireless power transfer. So there have been actually a lot of interest in doing wireless power transfer with the basic hope of being able, for example, to charge your laptop as you are sitting here right now without any need for a wire to connect to the wall. And so in particular, there is a very nice experiment published in 2007 to show that you could actually do a mid-range wireless power transfer with a distance of about a meter or so efficiently. And so in this experiment, what they did is they used two coils, both of them resonant, to allow power to go from here to there and to light the light bulb. Now, there are a number of things that are actually quite interesting about this experiment. One of them is that this does not require line of sight. These gentlemen very intentionally just sit between the source coil and the receiver coil. The other thing is that the field that carries the power from the source to the receiver is the magnetic field. And magnetic field interact very weakly with human body. So to light, let's say, a 40-watt light bulb, that was what the light bulb is at the time, you most likely would not want to touch the wire that drives the light bulb in most cases, but they were actually standing right in between. And I knew these guys actually very well, and they're still very healthy now. So this is 10 years afterwards. So, so at least this is one proof of some aspect of this. So it was certainly a very nice experiment and generated a lot of interest and has been commercialized. Now, in spite of its success, there is actually one aspect of the experiment that can be further improved upon. And that has to do with the robustness of the experiment. So as it turned out, what they did in the experiment, they showed this very nice curve of efficiency as a function of distance. But what they actually did for each of the distance is they have to retune the system. And that's actually intrinsic in the setup that they did. So this is analysis that carried out by a group at Intel. They basically show that, well, you can think about the system basically as having two resonators, having an input port and output port. And these two resonators basically couple to each other. So, and you have a radio wave frequency source driving the system to transfer the energy to the other side. Given that this is a coupled oscillator system, if you plot the transmission as a function of frequency, in the what's called the strong coupling limit, when the two coils are relatively close, then you basically have two resonance peak, and the peak transfer efficiency reach 100%. So that, of course, is very nice. It says that you can actually transfer energy over a distance through thin air. But as you vary the distance, because this is a coupled resonator system, the peak actually shifts. So in fact, as you increase the distance between the coil, the coupling constant goes down, and so the peak actually move together. They eventually merge, and then you get out of the coupling, so the strong coupling regime, in which case you no longer have high transmission. So in this case, what you see here is that within a certain distance range, for every distance, there is a frequency where you have high efficiency transfer. So for every distance, if you retune your circuit, for example, by readjusting the source frequency, you will have near unity transfer efficiency until you are out of the strong coupling regime. So you basically have the efficiency as a function of distance that look like this, where you have a flat region, which is very nice. And that's what they have shown experimentally. On the other hand, if you do not allow tuning, in other words, you want to use the same circuit for every distance, then in this case, what you can see, for example, if you fix the frequency here, then the efficiency at low distance, in fact, is low, and then it reaches a peak and then drop. In other words, if you don't do any tuning, you will only have a single distance over which you can have efficient power transfer. Now, for a stationary situation, for example, if I'm trying to charge my laptop, this is probably not a major issue. You can always tune it. On the other hand, there are certainly applications where you would like to be able to do dynamic charging. As one somewhat speculative idea, you may actually imagine that you have an electric vehicle driving on a highway, and you can actually charge energy into the electric vehicle while it is driving. And that would essentially allow you to, let's say, drive to Los Angeles without ever having to worry about your battery running out of charge, for example. Now, in those cases, then, it actually has become, and people have demonstrated, it has become quite difficult to do this continuous tuning circuits. So one of the ideas that we realize is, in fact, there's a simple way to achieve a robust wireless power charging. So the idea here is that instead of do this, where you have a radio wave frequency source to drive the two resonator, what you should do is to put an amplifier inside the source coil. And in doing so, the amplifier actually is going to generate its own frequency, though this becomes an oscillator. And what we show is that this gives you a way to do high efficiency power transfer without the need of any tuning circuit. The physics of this actually is related to some of the fairly recent development in optics and electromagnetics in looking at systems that has balanced the gain and loss. So this comes under the name of what's called parity times symmetric system that I'm not going to go into great detail in this audience. But I will just point out that we build upon these parity times symmetric system, but also by considering the amplifier to have a gain saturation. So one of the interesting things about the system is that if you put a gain inside the source coil, then if the gain is high enough, the system is going to oscillate. And the frequency at which the system is oscillating is exactly the optimal frequency at which high efficiency wireless power transfer will occur. So in other words, it's the system actually, if you configure this way, will automatically lock into a configuration that enable high efficiency wireless power transfer. So as a result, I show you this conventional scheme without tuning will have an efficiency curve as a function of distance, having only a single distance at which you have high efficiency transfer. But on the other hand, if we do what we do, which is to put an amplifier on the source, then you will get a flat region as a function of distance. And this is something that we have recently done the experiment. So the copper thing here, the thick copper plate here, is the inductor. And the white thing underneath here, the capacitor. So they together form the resonator. The source side has a amplifier built in, and that was the gain side. The receiver side has the load, and in this case, we put a light emitting diode underneath the receiver so that you can see the power that's being transferred. As I mentioned, in the conventional scheme, you will only have a single distance at which you will have high efficiency power transfer. So here's the experiment. Sid, who is doing the experiment, is the graduate student in my group. So this is the conventional scheme. As he's pushing apart, what you can see is that the LED lights up, but only at a particular distance. He's going to push it back. You can see that the LED lights up, but only at a distance. And then if you get close, the lights goes off. Okay. So that means that there's only a particular distance at which you can do high efficiency transfer. On the other hand, our prediction is that if you do the scheme that we do, then you will actually have high efficiency transfer in the range, even when the thing is moving. And this again is Sid. So let me see if I can get this to work. Okay. So he's again going to push the coil apart. You can see that the LED lights up right away over a range of distance while the thing is moving. And then it goes off when it's too far. And he's going to push it back. And again, you see the LED lights up and remain lighted as the coil is moving over a range of distances. And so it's a direct visualization of the robustness of the wireless power transfer in the system. And we actually measured the efficiency as a function of distance for the system without any tuning, and you indeed see this transition from near unity efficiency over a range until you get out of the strong coupling regime. And if you look at the oscillation frequency, the transition here corresponds to the bifurcation of the frequency that actually is what the theory predicts in this what's called the parity time symmetry phase transition. So this is actually an initial step in thinking about building the possibility for dynamic wireless charging. And we are now actually further optimize the circuit to improve the system efficiency further, and also to try to drive this to higher power level. So with that, I'm out of time. So I would like to summarize. What I hope to give you is a sense that you can do a lot of interesting things in energy space by seeking to control electromagnetic field. And this is really carried out by a very large number of students and postdocs in my group in the past several years. And I also like to thank ARPA-E and also GCEP for supporting many of these projects. So let me stop here and thank you.
Well, that was truly amazing. We have time for a few questions. Any student questions? In the back? People don't know what to say at this point.
Yeah.
Sure.
So this question about the PIN diode you just mentioned that can produce electricity due to the temperature shift.
Yeah.
So do you ever try the cyclic properties of such devices?
The what property? Sorry.
The cyclic properties.
Cyclic properties.
Yeah. For example, if you just cooling down and then go back and then cool down again, so will it just remain the stability?
I believe so. We did not do the experiment, but I believe so, because the optoelectronic physics here is very similar to a solar cell. So I don't think that would be an issue.
Was that John Fox and then Ari? John.
Yeah, I just have a question about the way you did the experiment with the optical chopper, looking at the radiator and the absorber. How come you don't see the thermal radiation from the chopper? It's in the field of view of the photoreceiver, shouldn't you just see that temperature?
So the chopper and the diode are at the same temperature.
Okay.
So they balance out. So that's why you only see the emissive surface.
All right.
I have a question about harvesting the dark current in the solar cell. Solar cells are generally designed to only accept current in one direction to prevent recombination at the contact. And in addition, modules include specific diodes so that current's only allowed to flow in one direction. So have you thought about the device physics for how to incorporate that into a real cell or module?
I think we have thought a bit about it. I think there, before we even get to that kind of level of engineering, there are actually other challenges. Maybe I should outline a few of them. That this actually requires a narrow bandgap semiconductor, and they typically have a lot worse radiative efficiency as compared with even silicon. So due to very large OJ recombination, for example. So in reality, the amount of power that you can get out of this approach is not very high. And so that's before one, let's say, consider many of the other aspects of detailed device engineering. Even if you just look at a Shockley Quasar analysis with non-radiative recombination. So what I meant to say is rather to present this as a challenge, because you do have, let's say, more than 100 watt per meter square of electricity that's sitting there, but there is actually no known device physics that can get you anywhere close to it. So I think that's a very interesting thing that we've been thinking about.
Other questions?
I have a question. So
We have four.
in your coupling,
Yeah.
in your coupling that you're doing electromagnetic, it's all near field,
Yes.
right?
Yeah.
And what would be really ideal is if you could go far field, resonant couple devices. And that is basically simply if you're on the microwave regime or the radio, microwave would be radar. Or if you have an infrared laser and have a detector again, that's a resonant couple device, basically. So when we were out there, we were looking at power transmission through radiation.
Yeah.
And it turned out to be difficult because of the efficiency of conversion. But those efficiencies are right now getting to be potentially 80–90%.
Right.
And if you have quantum devices on both ends, or quantum dot devices, you can have very high efficiency. So what about putting out infrastructure? For example, we go to Haiti right now, putting up a grid is difficult. But if you have a relay station with microwave or
Laser.
IR laser,
Right.
why not have transmission that way?
I think it's a very interesting idea. This, in fact, a number of people, a number of things have tried, but I think thinking about it as a fundamental way to redo the power infrastructure is very interesting. In our work is more close, so that requires line of sight. That kind of technique requires line of sight, which is a bit different from what we're doing. So I don't think we could generalize what we do here to that kind of application. But I think, let's say, a laser detector system for power transfer as thinking about the grid is very interesting.
So we have Alex, Sally, and
With regard to, actually, line of sight would be killing a lot of birds. We already do that down in Denver.
Really,
Solar system.
flux can be pretty low.
But at any rate, so you're coupling the two coils, and you got an amplifier on the one input coil, whatever. Isn't that just a super regenerative transmitter receiver set up from the 1920s?
Yes.
Thanks.
In fact, even in the wireless power transfer community, when people were doing medical implants, there have been related work on putting amplifier on one side. But I think the novelty, what we do here, I think are twofold. One is really to do that at the kind of scale that we're talking about. And the second is, in fact, this connection, which I actually, as a physicist, I find it fascinating. You can read those papers. This connection to what's called a parity time phase transition really bring a lot of clarity into why the system actually works this well.
Well, both coils couple to each other. I mean, it's electromagnetic.
It is electromagnetic, but the point is that the amplifier allow you to have a automatic feedback mechanism.
Sally,
My question got answered.
how efficient? Sir, right behind Tom.
What happens when you have more than like 2 coils in the system, or if you have like off-axis interactions and it's not perfectly aligned?
Off-axis is not an issue. In fact, we haven't done the experiment, but we have numerical results showing that, because what enters into the physics is just the coupling constant between the coil. So if you move this way, the coupling constant also decreases. The bar system is generally robust to that kind of decrease to a certain degree. So that's not the issue. The multiple coil interaction is a very interesting problem, and that's something that we are thinking quite hard about.
But we have time for one last one.
You demonstrated high efficiency in your last section, but not how high power transfer. What limits that?
We were powering an LED there. So the amount of power can't be that high. I think it's a few milliwatt, what we have done. For the stationary system, like the MIT system, people have scaled up to maybe even 10 kilowatt level. And I think in principle, we can imagine that we should be able to scale up into that level as well. So people are actually doing stationary car charging with that system already.
Why is it difficult? Do the magnetic fields get to be too strong? Or?
No, it's just the power electronic circuits are, you just need to build a circuit to be able to handle that kind of power level. And that's not, we have never done that, so it's not entirely trivial either.
Great. Well, I think we're out of time. Thanks for an inspiring talk and stimulating discussion.